the USA decided not to pay for Martin's experiment. He became a globe-trotting scientific evangelist for the idea of a compact plasma.
I began to give talks about this idea and how it may be very interesting to study it. And I visited Cullum a couple of times since then, and I think I got Alan Sykes very interested in looking at this.
I was the person jumping up and down saying, why doesn't somebody build one of these things? Because theoretically they look to be a lot of advantages. There are two ways of doing that. Either have a major project and lots of review committees, and 5 years down the line you may or may not get your money. Or if you have enough bits and pieces and just a bit of sort of petty cash, you could try throwing just a test of the concept together.
That test of the concept is what the reunion is all about.
Alan was charged to create a presentation for spherical tokamaks.
To be chairman of that group.
Aha, you volunteered, very commendable. And
well, it was either that or getting involved with something I wasn't interested in.
Right. Good piece of volunteering. And the spherical tokamak won the review, hands down. And so our division head at the time, now the director, Derek Robinson, said to his department managers, about 5 or 6 of us, right, you lot, I want you to give me a cheap way of building a spherical tokamak since it's won this review.
Some people have done some theory in the States, some people at Cullum have done some theory, it might work. But everybody said, well, we don't know how to do it though. It's all very well saying, let's have a nice spherical system. How would you create one in the first place? How would you make it? It's all very well saying you could do it, but how would you make it?
And the only person that came back in the next few days and said, this is how we might do it, sir, was me. And I sketched it on a whiteboard, and he said, you've got the colloidal field coil layout wrong there because flux conservation means blah, 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 blah. So he said, do it like so-and-so. So I played around a little and said, oh, you mean a bit like this? And he said, yes, that would now work.
But then the big problem, as usual, was where are you going to get any money from? And then we realised we got a real problem because government said, no way, this is mad idea. Our European colleagues said, go away, we're not going to provide you with something with a mad idea like this, it won't work.
The idea of having a plasma, a metre across in the middle of a large tank, they thought the plasma wouldn't stay there to be unstable because conventionally you have a fairly close-fitting shell that surrounds the plasma, and we weren't doing that.
The Sun keeps its plasma under control with its enormous gravity. No gravity, no fusion. The core of the Sun is at 15 million degrees. The hydrogen atoms break down into a mixture of electrons and nuclei, a plasma. The nuclei repel each other, but the pressure forces them together. They fuse to form helium, and this releases energy. The plasma conducts electricity so it moves to magnetism, into patterns on the surface of the Sun. The Cullum team wanted a machine to discover how to control plasma on Earth. It's a trick which needs lots of electricity and huge magnets. With no direct government money, the team needed an ingenious way to put the machine together.
I visited Alan Sykes at home several times, and on one occasion I remember going upstairs and discovering that the whole bedroom was full of car bits. It was that he put cars together, and motorbikes actually as well, from bits and pieces, and realised that one of our key modelers, more theoreticians, actually had a practical bent and could put things together. And I thought, that's just what we want.
People thought that the techniques I used for that, scrounging from scrapyards and things, would come in very useful.
Construction began in 1989, 50 miles west of London, with no official government funding.
I don't think we got anything literally from a scrapyard. It was the care and custody store, it was called, where people's favourite bits of kit from past experiments were stored away. And so we raided that. It was a sort of a scrapyard of Cullum.
The team also needed Tom Todd's input to help them build the machine, but his expertise was in demand elsewhere.
During the daytime he was very busy with meetings, but at lunchtimes we realised he would have an hour off for refreshment and recreation. So we started meeting at lunchtimes in the Machine Band pub, where we would have a drink and a lettuce leaf or two, and he would look at the drawings we'd made up and advisors on how to get the machine built.
You would go to the machine man, spread the blueprints out amongst the beer and the ham and veal pies or whatever, and using the beer bottles to hold the corners of the blueprint down, we'd argue about sections of copper and vacuum pump speeds.
We weren't supposed to be using government money at this stage for building this device. And of course, it's a sort of nice, relaxed atmosphere. And that's how Alan likes to do things. It's not so rigid and formal like we might have with our project planning meetings actually here.
In 1991, after many working lunches, the machine was finished. It was called START, short for Small, Tight Aspect Ratio Tokamak. It's a remarkable collection of spare parts.
The vacuum tank, for example, was used in an experiment in the 1970s. It had been lying unused on the runway outside the lab since then. It's an aluminium tank in sections, so the vacuum conditions aren't particularly good for plasmas. But still, we got very good results with it. It looks a bit Heath Robinson construction. These wires over here look rather tatty. You can see signs of leak seal being put on there because when we had a leak, we just put some spray leak seal on.
No one knew for certain it would work. Fusion research has had its share of failures. But it worked spectacularly well. A high-speed camera revealed a delicate cloud of hydrogen plasma at 5 million degrees. It lasted just long enough to take measurements.
Oh, that was exciting. That was really very, very exciting to me. And of course, a little bit of envy in there that we couldn't do it in the United States. The first plasma suggested that the basic idea is basically sound. It can contain high temperature plasmas.
Once the machine was shown to work, official government funding became available, and the team began detailed research.
Well, the physicists would say what they'd want, and it was my job to give them what they wanted. And then the physicists would come and say, the bloody thing's broken down, and I would have to go in and fix it.
I was dragged in very informally. I wasn't allocated a particular job, and Alan was very, very good at capturing people and getting them to bring equipment along so that he didn't actually have to spend any money.
The team found some unusual ways to stretch the budget.
This is the world's first spherical tokamak, a picture of the plasma in there. This is actually a picture taken with a sort of glorified ordinary camera with a mechanical shutter. And so there's a bit of a delay on the shutter, even though you trigger it precisely electronically. There's a few tens of milliseconds delay. And so we made many blank films because the plasma discharge only lasted about a 20th of a second. But if you take them to Boots on the sort of 1 hour service, they didn't used to charge you for blank films. So Marcus used to go on his motorbike to Boots and Decote at lunchtimes, and sometimes he'd come back with some pictures and sometimes he'd come back with a blank bit of film.
Even Martin Peng came over from the States to lend a hand.
Well, once the experiment is getting going, it's impossible to stop me from visiting Column every chance I got.
Martin was keen to increase the power of the machine. One way to do that was to heat up the plasma with a special particle beam. There was a spare system in the States.
Derek and I was just chatting during this meeting. I said, gee, wouldn't it be nice if we actually bring over a neutral beam system to put on START that will give it some additional heating? And that's how it happened.
It's about the same size tank as START is itself. But this injects high energy hydrogen into the plasma, and this heats the plasma inside the tank. And by doing this, we're able to get very high pressure inside our plasma, and we're able to get a world record value of a sort of an efficiency parameter, which is the amount of plasma you can hold for a given magnetic field. And we got 3 times higher than any other tokamak had got in the world, and people were really amazed at this.